Um, so we started out with the dot product. Then we use that to define work with that line integral. If you're lucky, the force is constant and you don't have to think about it as an integral. You can just use the dot product. That's much preferable. No, I just work, not integral. And then we talked about kinetic energy. And then we used work and kinetic energy to define the work energy principle. Hey, Nick and Jace, will you guys not talk, please? And the work energy principle is sort of the general one. This is the one that everything else is built off of. And that's where we are so far. We've gone through all these. The work energy principle always works, and we'll see that that's the thing that turns into conservation of mechanical energy under certain conditions. Now we're going to define potential energy, which is a really interesting thing mathematically. We'll see connections to forces, connections to work. And this only works for force fields. What's the potential energy of a force you can't express as a force field? It isn't anything. It doesn't make any sense. So a potential energy is only defined for a force field. And then once we've done that, we'll talk about conservation of mechanical energy. This is the general one. This is a special case of the work energy principle. Okay. So that's what we have to do now. So for potential energy, okay, this is the overall topic. And potential energy is only defined for force fields. And force fields are also known as conservative forces. The idea of both of these force fields and conservative forces is if you tell me the location of an object, that's enough information, and I know what object you're talking about. So like we have to know the mass of the object and whatever, the stiffness of the spring if we're talking about springs. But given that background information, if you tell me the location of the object, that's enough for me to know the force that's applied to the object. Okay. So force field and conservative force both mean the same thing. and that is that if you know the object's location, that's enough to determine the force applied, the force applied to the object. For us, there are going to be two physical examples, and then there'll be some problems that are sort of more mathematical too. But the two physical examples that we'll use are first the weight force, and second the force applied to an object by a spring. Okay. So let me take a second and give a couple of kind of intuitive examples of what this means, like to make sense out of how those are different from other kinds of forces. So let's first, well, first we'll think about the weight. Do it with this remote control. So say we know the mass of this. Okay, it's 0.1 kilograms or something. And if I tell you the location of this object, excuse me, is that enough information to calculate the force that gravity applies to it? Actually, the way we've been dealing with gravity so far, when we're close to the surface of the Earth, is you don't even have to tell me the location. That's more information than we need. But that condition still holds, right? I mean, you tell me this is over here, sitting above the chair at a height of 5'6" or whatever, and I can say, okay, the force is down with a magnitude of mg, so we know that force vector. It actually turns out that gravity depends on the distance from the center of the Earth. We'll talk about that briefly later on, but still, even using that more complicated formulation for gravity, if I tell you that we're at this location here, we can calculate the distance to the center of the Earth and calculate that force. Yep. Yeah. Yep. But it doesn't, since the radius of the Earth is so much bigger than the variations in height people make on Earth, it just doesn't vary much at all. At the top of Mount Everest, it's like 2/1000ths of a Newton less or something. I guess a meter per second squared less in the acceleration. Okay, so it works for gravity. Now let's think about the force applied to this by a spring. Okay, so we're going to choose the spring. We're going to choose where it attaches. So let's say I have a spring that's a certain stiffness, and I attach it to the wall. Okay, and attach it to this, and now I move this thing around at any location. So say that it's here. I can calculate how long the spring is, and use that force equation. The force applied by the spring is equal to the spring constant times the change in length of the spring. And so I can calculate that force. Okay. So one requirement here, one way to think about these is it doesn't matter on the path you took to get there. There's path independence. If I move this around and then put it here, gravity's applying just the same force to it as if I did this path and went there, And the same with the spring. If I do this back and forth 100 times, the spring is still applying the same force here as it would have if I wouldn't have done that. It's independent of the path. It only depends on the location. So the connection to that, between that and the idea of a force field, like how is that a force field? You can, that idea, conservative force, the fact that all you need is the location, you can sort of think of that as there are all these sort of latent force vectors sitting out there in space waiting for this thing to come over and activate it. You know what I mean? And so you can think of every spot having a force vector just waiting for this to come and turn it on. You know, so this comes over here to this location, and the force vector that was waiting there is like, oh, it's my turn to shine. You know, and so it applies this force mg down. So that's the idea of a field, like a field of poppies. You know, like everywhere I go, there's a poppy. You know, I can make drugs out of them. That's the same idea as a force field. Wherever you go, there's a force there waiting for you. That's why they call it a force field. Okay, let's think about some things that are not conservative forces. Okay, so first let's think about a normal force. So let's say that we want to figure out the normal force that the table applies to that remote control. In this location, your first thought might be like, oh, well, if it's in that location, the weight's pulling down, it's in equilibrium, so the normal force is equal to the weight, but going up. Dang it. But if so at first thought, you might think of that as a conservative force, but without moving it, I can push down on it, and that increases the contact force with the surface. And so now at the same spot, there are two different normal forces, right? The normal force is not totally determined by the location. Any questions about that? You understand what I'm getting at there? And now let's think about a friction force. That's also not conservative. That's not a force field. The easiest way to think about that is think about this thing sliding to that point, moving that way, right? When it passes here, the friction force is this way. And now think about it sliding from the other direction, same spot, and the friction force is the opposite direction. So normal force, friction force, those are not conservative forces. You can't think of those as force fields. There's no force waiting there at that location. The force that's applied depends on more than just the location. Okay. Other examples of field forces are electric fields. You know, it's the same idea. If you put a charged particle in an electric field, you know the force it applies independent of the path it took to get there. Magnetic fields are the same way. You put a piece of iron or something in a magnetic field, it doesn't matter about the path it took to get there. It doesn't matter about anything else. You know the force that that magnetic field is applying to the object. So for conservative forces, which is the same thing as saying force fields, there is a potential energy function that depends only on the object's location and properties of the object, properties of the spring, that kind of stuff, but depends only on the object's location. It doesn't depend at all on the path the object takes to get there. So first, gravitational potential energy. And I'm going to represent potential energy always with a capital U. And I don't know why. I didn't make that up, though. Um, so capital U gravitational is equal to the mass of the object times g times a height h. Remember that this g is a positive number. I was about to say up. That's not right. It's positive. And the height, if you think about that for a second, you're like, well, what are we taking the height relative to? The top of the table, or the floor, or the center of the earth, or the center of the sun, or the center of the galaxy? You know what I mean? Like, there's not really a obvious choice for your zero height. Um, that h is based on an arbitrary zero height, as long as you use that for the entire problem. That's chosen for the problem. Obviously, you can't choose an arbitrary zero height for every calculation inside the same problem, or your potential energy would be zero for everything, and it wouldn't be useful. Based on an arbitrary zero height chosen for the problem. Okay. And for springs, oh, and I said that so the potential energy function depends only on the object's position. In this case, that height is what tells us about the object's position. And now for a spring, so the spring potential energy function is equal to 1/2 times k times delta L squared, where delta L means the same thing it did in the spring force equation. This is the difference in springs, in the spring's current length from its resting length. How far it's stretched or compressed from its resting length. So based on an object's, so if you're given an object's position vector, you can use that to calculate the height of the object and calculate its potential energy due to gravity. And you can calculate the stretch or compression of the spring and use that to figure out the spring potential energy. All right, well, why do we want to introduce this new thing? We already have this totally general expression that lets us do calculations in terms of energy, the work energy principle. So why introduce potential energy? It has two useful relationships with other variables that other quantities we often want to know. The first one is over any object path through a force field, the work that's done by the force field on the object is equal to the negative change in potential energy. And since usually calculating potential energy values for an object is easier than calculating the work directly, this is a way to get the work in an easy way for certain kinds of forces. Okay? So this is usually a much easier way to calculate the work. And the second important relationship is that a force vector that's applied by the force field is equal to, okay, get ready for this, the partial derivative of the potential energy function with respect to x. That's an x component. The partial derivative of u with respect to y, and then both of these are negative. I guess I'll put it in here. Okay, so most of you haven't seen partial derivatives in classes yet. You've seen them in movies because this is movie makers, to save half an hour of convincing you that someone's really smart. They just have someone write partial derivatives on a mirror or a window with a marker, and then you're like, oh, I get it. This guy's like a genius. It really isn't that hard. But if you ever want to seem smart to people, write those on a window. So, well, that's pretty cool. Interesting. Notice that the potential energy function is a scalar. It's energy, and all energy things are scalars. They're not vectors. But you can use this scalar thing to calculate a vector. So this quantity that doesn't have any direction to it, it holds this directional information inside of it. You know, sort of interesting. And one consequence of this is at any location a force field applies a force, applies a force vector toward the steepest decrease in potential energy. Okay, so the forces in a force field, you can think of it as a force field is always trying to reduce potential energy of an object, okay? Let's think about it in terms of gravity for a second. So the potential energy function due to gravity for some object is equal to mg, times the height. Okay, so down here it has a little potential energy as it rises, and it doesn't matter where horizontally it goes, but as it gets higher, its potential energy goes up. Okay, that means as it goes lower, its potential energy goes down, and at every instant, the weight force is applying a force vector toward a decrease in potential energy. Okay, gravity is trying to make things. If the only thing acting on this thing is gravity, gravity is going to make its potential energy decrease. Okay. All right. What about these uh, partial derivatives? So partial derivatives are the one with the curly D's. Derivative. And all it means is, so d, whatever, let's call it df dx just means treat x like a variable and treat the other variables as constants. Okay, so as an example, let's say that we have some arbitrary potential energy function that's equal to 50 x y squared. Okay, what's the force vector applied by this force field at the position, let's say 2 meters in the x direction, 3 meters in the y direction? Well, the partial derivative of u with respect to x, we're just going to treat that y like it's a constant. And so this is just going to be equal to 50y squared. Okay, you with me on that? And then the partial derivative of u with respect to y, we'll treat the x like it's a constant. So that's going to be 2 times 50 times xy. Yep. Okay. And so that means that the force vector is negative 50 y squared, negative 100 xy, because you have to apply that negative for the force vector, evaluated at the location 2, 3, x equals 2, y equals 3. And so that is negative 450, I think. And then negative 600. Wait, is it negative 600? Oh, yes. Okay, so yes. That would be complicated. Like, so you would have to you'd have to choose how fast it was going at the instant you started, the location where it started. You'd have to calculate the direction of the force. From that, calculate the acceleration and then integrate it. I guess, it'd be sort of tedious. I guess it wouldn't be that bad, depending on the functions. But that's not something we're going to do. But yeah, that's a valid question. And actually, when you see when you take physics 2, not from me, you will do a lab where you measure the ratio of charge to mass of an electron. Electrons are really little, like you can't put them on a scale, right? And so you have this machine that shoots out electrons, and you can see the beam of electrons. And then you apply an electric field to it. And based on that, you do exactly what you're mentioning to calculate, well, that electron potential energy function depends on the charge and it also depends on the mass. So you use the curve of that beam when you apply this electric field to it to figure out the charge to mass ratio. So there's some cool applications of that, but we're not going to do that in this class. And now, because of the, so to derive the conservation of mechanical energy equation, suppose that all the work done on an object is done by conservative forces. Then the work energy principle, remember that says that the total work is equal to the change in kinetic energy. But now if all of the work is being done by conservative forces and we have potential energy functions for those, we can replace the work with the negative change in potential energy. And so you can think of that as negative u at instant 2 minus u at instant 1, and you can think of this as the kinetic energy at instant 2 minus the kinetic energy at instant 1. And then rearrange it, and you get conservation of mechanical energy. The kinetic energy at instant 1 plus the potential energy at instant 1 is equal to the kinetic energy at instant 2 plus the potential energy at instant 2. And that's just so easy to calculate if you have those potential energy functions. So in words, this says call the kinetic energy plus the potential energy mechanical energy. If no work is done by non-conservative forces, then the mechanical energy is the same at any two instants. It's conserved. So the mechanical energy is the same at any two instants. It's conserved. Okay, well, how often are you going to have problems where the only forces acting on something are gravity and spring forces, and maybe magnetic fields and maybe electric fields? I mean, I guess there are some. I said that electron example, that's one. But here's the key thing that's going to help us a lot. It also can include normal forces and centripetal forces, because even though those forces can be non-zero, they don't do any work no matter what they are. Okay, so notice these problems can still include normal forces in rolling and sliding, and centripetal forces in circular motion. Okay, so let's see a few examples. I'll start with a few examples that would be such a pain to do with Newton's laws. You could do it, but you'd have to know, well, it would be a real pain in these instances, but it's a one-line calculation with an energy approach. So the first example, let's say that a person's at the top of a little hill on skis, getting ready to enjoy some mid-April weather. Let's say that this hill is 2 meters high, just a little bump. It's like Buck Hill. And let's say the skier starts at rest, if there's no friction, what's the speed at the bottom? Okay, well, let's think of a free body diagram at some point in this path, just to make sure that we take all the forces into account. Um, so what forces are acting? There's a weight force of mg down, and there's a normal force, N. This is conservative. That means we have a potential energy function for it. This is non-conservative, but since this is a sliding problem, it does no work. And so because of these, we can use conservation of mechanical energy. So I'm just going to consider the top of the hill instant 1. And the bottom of the hill instant 2. And at each of these, we have to calculate the potential energy. If you have different sources of potential energy, you just add up all the individual sources. We have gravitational potential energy. That's equal to mgh. In order to come up with h, we have to choose that arbitrary zero height, which I think you can choose it wherever you want, but I think most people would choose the bottom of the hill. You get the same answer no matter where you choose it in the end. And so that's mg times the height is 2, right? And then we have to calculate the kinetic energy at this instant. That's 1/2 m times speed squared. He's starting at rest at the top, so this is equal to 0. Questions about what I'm doing here? Yeah, 0 speed. Yep. Yes, I should keep calling it the same thing. Thank you. It is capital P. And then at instant 2, the gravitational potential energy is mgh. This time, what's h? 0. The kinetic energy is 1/2 mv squared. This time, we're trying to find that v. So I'll just leave it in there so we can solve for it. Conservation of mechanical energy. Come to me. 2mg plus 0 is equal to 0 plus 1/2 mv squared. You can divide both sides by m, and that tells us is that the mass of the skier doesn't matter. You get the same answer no matter what. And now we're just isolating v. So we have v squared is equal to 4g. And so v is equal to 2 times the square root of g. And can someone calculate that? Square root of, I think maybe that's 3.13, and then 6.26 meters per second. So if you try to imagine how hard that would be if you were going to calculate the forces and go through Newton's laws and whatever, it'll give you a headache to even imagine, but this is like a 2-line calculation. You'd have to calculate, you'd have to come up with some expression for the function of the hill. Like, notice it didn't even matter what the shape of the hill was to us. But for that, you'd have to come up with an expression for that, figure out how the normal force direction changed depending on that, figure out blah, 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 integrate your answer. It would take forever, you know. Yes? Let me look over the problems that I have and think about it. If it is going to be on the test, we'll spend lab tomorrow getting ready for it. Okay. Okay. I'm not, I'm sorry, yeah. Mhm.